So hello everybody. Let us know if you're online and ready to work. Please drop in some comment in the chat. I think today the internet connection must be much better, hopefully. Like I got connected via cable, so it should work fine. So yeah, please get the template 15.2 or get it from the link in the mega. So is the 15.2 template ready for work? You already see one plus coming in. So today there's going to be really interesting type of model that we will implement that is right now kind of state-of-the-art model for the language modeling task. We will look quickly at one example of that. But primarily we'll look at the mathematics of it. So this is for the time series, but actually you can also use it for images and all sorts of things. Like there is the vision transformer for the one way how to do that for the images, but seeing that paper, implementing that, I definitely see that there is going to be much better models soon, or already there are. They are just not yet confirmed for publication, most likely. So, but anyways, any of you who want to do research can try to do something in that direction as well right now, especially for the images and other types of neural network models. So we already looked at this kind of configuration once before when we were developing the LSTMs, the time series with the long short-term memory cells. So then in this gray area, it was replaced by RNN, and the input was projected with the lookup table and then transposed and dot product for the output. So that's what we already saw. But now this kind of model. This is a OpenAI GPT version. The initial first version that was for the attention models was a little bit different, but also a little bit more complicated. So I don't want to do that version actually. So for at least in this course, we will not be able to properly investigate it. So the attention is all you need, and the BERT type of models, those that come from Google and TensorFlow, they look like this. So this is attention all you need, BERT, Google. So that was actually one of the first papers. Again, this is the same kind of architecture as in the first slide. The only difference here is that for the output, there is another set of the transformers that are working with the kind of previous outputs plus the hidden states from the encoders. Makes it really complicated, but it works also. So like the GPT model, which the latest one of GPT-3 that is not much different from this, is like really powerful, and kind of I would say that it's like not necessary to implement the BERT. So let's examine step by step what's happening here. So actually I like this image. The main source of everything that we're going to talk today is this orange part here. That is a self-attention block. We already know that there exists the ResNet blocks and all sorts of blocks that we use for building models. Even like LSTM cells and stuff. We know about normalizations. We know that we can add skip connections, and the pointwise feed-forward network, that's just in this case any kind of non-linear small neural network or even multi-layer perceptron. So don't worry right now about this part. So we'll just start looking at the orange part. And the orange part is actually also here on this same slide. Maybe we can use the same slide here. So the orange part is these equations. Again, first we will try to implement this equation and then only this one. So the multi-head attention is just the same equation repeated multiple times. The equation itself looks like this. And we will also look at it visually in multiple ways, trying to help you understand. So there are three parts. So the query, key, and value. So there are the query, key, and value. Again, all of these things can be defined in multiple ways. It's not that there is a one formula for the getting key, query, and value. It can be even smarter models. So today, when we talk about transformers, there are so many small parts that can be used as a research topics. There's like even from very beginning, like you can start like exploring all sorts of embedding, like deep metric learning models or embedding tables or something for the keys and values. I actually have seen already some similar models like that. So but in general, the easiest way how they do this is that they get the encoded x value for every time step, right? So let's ignore right now the batch dimension. The batch dimension is there, but we will not think about the batch dimension at all, because batch dimension is just repeated stuff there, right? So the x at every time step, right? Remember that the full x consists actually of the full x consists of the batch that we ignored, then the sequence, and then the features. So the features are coming from the embedding table, if you remember, right? So like for every word, like the word in the sentence, in language modeling tasks, we have a vector that is representing that word. So there is batch, sequence, and features, and then the xt that is for every step in the sequence for single element of the batch, or you can repeat it over all of the elements of the batch. So we get that x, and we pass that x through some kind of small linear projection, or it could again be some research topic, or maybe there is a better ways to do this. So what you do is here a linear projection, and the linear projection should produce these three values. So you can actually, if you want to think, you can have three linear projections. So from the same x, you get three different vectors. So with the transformers, the most important thing to understand that the hidden size, remember the embedding hidden size, right? That is all over the whole, like whole transformer. Like we almost never, or let's say never, change the hidden size shapes. So like if you remember convolutions, then we kind of increase the depth of the hidden size, but here we are sticking with the same one. So that means that the x here coming in, the input features are the same as the output features, and it generates the query. The input features have the same as the output features, gets the key and the value. So those are just the linear projections from the same x input. You get three different vectors. So when you have those three different vectors, you insert those vectors into this equation. So maybe I should somehow point which part we are talking about. Why don't I see? Okay, I see this. So the orange part here, this one, is this thing here. So the x's, we converted the linear layers to get these key query values. Then we do here the following. So if we look here, there is the first the first there is the dot product between the query and transposed keys. So that's very important, transposed keys. Without transposed keys, everything falls apart here. So here actually in this equation, this is not like really emphasized, but this is very important. There is a transposed key here, and also like in the multi-head version as well. So that is one. Then we have some kind of scaling operation. The scaling operation, again, like not very scientific way to do this. I think they had some proof of why they do this. So that is the square of the dimensionality of the embedding. So they just have a little bit of scaling, but the softmax at the end also does the scaling itself. So the softmax then gives you attention matrix. So this part, let me emphasize that with the color. So this part of the softmax, also the same thing is here. So all of this part is the same equation. Gives you something like this. Let me find you. Maybe I will also drop later the same image a little bit larger. So that gives you like a matrix. So let me, I will add it here, a small version here, and the next slide a bigger one, so you can understand a little bit better what that matrix is actually. And we will also try to draw the idea, so because maybe that transposed thing is not super clear. So the idea is that you have some kind of matrix that allows you to look at the current word, so the current word in the sentence. So in this case, let me check what's in this case the current word. It seems a little bit strange, if I'm honest. So we will see our own matrices. Our own matrices will be better. So I mean, if you have the first word it, and then the second word should, then it has the option to look at the only about the first and second word, and there is not allowed to look at this word. But I guess in this case it's allowed to look at the next word because this is a translation task. So this is if you have a sentence and then you have in a different language the output. So maybe in this case that's acceptable, but in many cases that's not acceptable for the language modeling task, because otherwise if we can look in the future, so you will see these matrices ourselves today. So if you look at the future, like if you are the step one, it, and you want to prognose the next word should, and you can look in the future, then you can just copy from the future the output and you will have 100% precise model. So you are masking that, so you're telling you cannot look here, you cannot look here, you cannot look here. And then for the second word, you can look only at these two. For the third word, you can look only at these three. For the fourth, you can look only on these four. For the fifth, you can look only on these fifth. So they are in that manner. I did not notice before that this matrix is a little bit not the way how it should be. So it's a idea that you're looking from this part backwards, so you cannot look ahead of the time. So after you create a softmax, so you create a softmax actually by dimension of, so let's see, so if this is the time steps, so the brighter the pixels, the more attention it pays to that word. So the idea is that, for example, if we are right now at the word, let's try to find some little bit better example. This is really bad matrix. I will try to look quickly for a better one. So let us see. Attention. language model. There's definitely better visuals. If I will not find it now, we will make it ourselves. That's definitely not a problem. But be nice to find it. It did not kind of notice transformer NLP. Let us check. Matrix. Depends really on the implementations a lot. Like, so if you are doing the translation, then you can look in the future. If you're not doing translation, should not look at the future. Or maybe I can find some of my own example. Just a second. I trained today some of the transformers for this session, and I had at least some of the examples that I can share. So they are really small. This one, let's see if I can somehow make it much bigger. Okay, so it's not great, but at least you can see the idea. Okay, it's trying to blur it. Anyway, so the idea is that for example, if you're going to the so this will be the time steps on this axis. So this is the current time step 0, current time step 1, current time step 2, and so on. And the other axis is the kind of attention for the same time steps, time step 0 till time steps n. So, and if you think about it, so at the time step 0, you can look only at yourself. For the time step 1, you can look at yourself and one time step before. For time step 2, you can look at this one, this one, this one, and so on. And the brighter is the pixel, the more attention it pays for that particular word in the sequence. And we do this for all of the samples in the batch. And we actually do this many times because there is the multi-head attention idea that we can split it even in more these kind of matrices. So I hope that makes sense. That makes sense, hopefully. And then when we have this attention matrix, we can do the dot product with the value vector. So the value is actually the value matrix, but we can think it as a vector probably. And then we get the attention, then we get actually not really attention, but already attention multiplied by value. This is the information. We get information. And here there is follows a couple of very important things. So one is that we have a skip connection here. So the skip connection is one thing that could definitely be improved. I have read in the papers that the skip connection should be removed to have better models, because otherwise it can just skip the attention part altogether. And depending on some of the configuration of the layers, it can happen quite quickly actually that it tries to skip the attention. So, and then basically if it tries to skip attention, then you see this pattern that it repeats the same word as in the previous time step or something like that. So then there is the feed forward network. So that's just a simple two-layer network. Then there is again addition, skip connection, and the layer norm. And then we do the same stuff as we did last time. And the one thing that needs to be noticed here is that this transformer block is repeated 12 times or even more times, so it's very deep. And also there is the multi-head attention that is in the H dimension, so there is, let's say 12 transformer blocks with 8 multi-headed tensions. That's quite a lot of things going on there. So that's one part of the things. Let's keep a little bit looking at this equation. So, and then we'll return to the last missing parts. So if you look at the materials that I sent you before, there are some really nice materials on internet, visuals how this works. So there is another material where you can see that like, so here the idea is that we have two-dimensional kind of embeddings, and if we would do this kind of dot product here, we would get 3 by 3 matrix for attention on every time step of 3 time steps. And then when we do dot product by 3 by 3 matrix by this matrix, we get back the same matrix as the shape of the Q as in beginning. So that's one thing. Maybe also you can think of this idea of not two-dimensional matrix. If you think of that as just one-dimensional, maybe that also makes sense. That, for example, if you have just like in the very beginning 3 vectors, like for the Q, K, and V, right? And all of them are the same length. So Q, K, and V. And then when you do the transpose operation, it happens like in that picture where there is the Q transposed by K, and that of course produces nice squared matrix, right? And that you can then multiply by this value part, and you will get out the same shape as the input, basically. So that's in the case of one-dimensional embedding. So it could be possible that you could work with one-dimensional embeddings, so that at every time step, so the horizontal is the time steps, so there's like time step 0, time step 1, time step 2, and so on. And the vertical is the embeddings. Again, another image from that source that I gave you, another way to look at this. So you can look at this a different way. So another way is to look at this. If we're right now at time step 0, we can access, if this is a translation task, so we can look in the future as well. So if this is a language modeling task, we should not look in the future. But if this is a translation task, it might be okay to look in the future. So then in this case, we can look at the K1 and also K2 here. So if you see that Q is not changing, Q1, so we are right now at the location of Q1 or the time step 0, that is Q1. But we are looking also at K1, K2, K3, K4, and so on. So that's one interesting part. By the way, okay, so this is divided by 8, right? So anyway, so we do that, and then when we have that matrix, so we do that, and then we divide it by 8, and then we calculate softmax, and then we have like attention. So to which of these words should we pay attention? And then you can think of it like multiplying the 88% with the value vector here, or the value vector is basically the same kind of like the x input. It's just like projected on different hyperplane. So and you also multiply this by this, and then you kind of sum them all together, like, but at the same time you always leave the same time dimensionality. So you see, if we got three time steps coming in, we get 3 time steps coming out. So that's not changing at all. So that's one thing. We definitely will understand this better since we start coding, but hopefully so far that's at least in some way understandable. If you look at the material that I gave you in the links, you will see that there is also visual representations how this works. So That's one. So there is missing another part here, super important part. So this thing would not work at all if there would not be any information about the actual time step. So as you see that we don't have any time indexes or something, so the model do not know that we are right now at time step 0, time step 1, and so on. So the only way how to do that is by using the positional embedding. So here there is maybe there's a different way to do this, by the way. So again, new research direction. Don't understand the paying more attention to words. Mm. Um, so maybe to understand this better is that so if there would be some kind of words, I want to eat apple, and here we have the same words on this part, and we want to predict the next word. So if we are at the location of, let's say, if you're at the location of eat, or maybe we're probably at the location of, let me think. Yeah, so we are location of predicting the word apple. So to predict the word apple, probably we are at the location of eat. So that means that we are paying attention to eat itself. So that this is quite bright. So let's say you're paying attention to 99% that I want to eat something. So then maybe we should also pay attention to the word I. So for example, eat can mean something else as well, like let's say people eat fruits or something like that. So if there would be first their word people or something, maybe that would not be that correlated with the apple. I don't know. Like, so if the model knows like if in the sentence there is something that kind of thinks that next word should be more like an apple, not like computer, for example, or some other kind of word, then it tries to pay attention to those words that try to determine the next word. So this was not probably the best example. I was trying to just generate something on the fly. So we are trying to predict the next word, the apple, and we are right now at the location of eat, and we are trying to pay attention to, for example, to these two words. And if the model has seen before a lot of people who say that I want to eat apple, so then the model will understand that these two words are the most important for predicting the next word, apple. And the one thing to notice here, this is very different to RNN and the LSTM. There is no memory at all. There is no memory. So these models do not remember anything at all. So the only thing that they remember is the like kind of placing together, like sticking together all sorts of words from the data set that you gave it for the training, and but it don't understand actually, so it don't remember the previous context and stuff like that. The only way how you can remember previous context is if you add the previous context to very beginning of the sentence. So for the LSTMs, you could run LSTM theoretically for thousands of words and then have the hidden state and then get the next word. For the transformer, you would need to add those 1,000 words here in front, and then you only can predict the next word. So it cannot be compressed into memory. It's just paying attention to the text that you already gave and try to guess what will be the next word. Hopefully that kind of makes sense. I really hope, like, if it still doesn't make sense, you can try to give me another question. So again, returning to this part. So this part is super important. in order for everything of this to work. If that part is not implemented, nothing will work. So there is the positional embedding. So that determines at what time step we are right now located, because all of the time steps look exactly the same for the model. It's because we pass them to the embeddings, and if you think about, you can just like eliminate the sequence dimension by multiplying this together, for example, and they would look all the same. For the LSTM, this is not the case. For LSTM, it is much different, because in LSTM we have, like, remember the first word, then we process, then we do the next word, then we process. In this case, we do everything at once, because we can parallelize these functions for every word in the sequence, for every batch. It doesn't matter. Like, we can do everything at once. We don't need to like do like step-by-step operation here. And the positional embedding, that's why it's very important. So great that it makes a little bit more sense that of those explanations. So by the way, again, there's a room for research. For example, we use the softmax, like the attention models use softmax, but it could be maybe norm max, it could be hard max, it could be actually like something like hard attention. There are a lot of things that can be researched. So positional embeddings, and again, positional embeddings, again, something that can be researched, because that's again not something that is completely found as the best way. So the most of the papers kind of advise on two directions. One direction is using these formulas. So there, I think the position is the index of position, and the D is the dimension, and the I is the location in the dimension. So, and if you apply that formula, you get these kind of matrices. They look something like this. And the idea is that the first, so in this case, the idea is that I think the time dimensions are on the, on the rows, most likely. Time, so here there's a time 0, time 1, and so on. And the embeddings are on the other dimension. So every time step have unique embedding that is not learnable. So not learnable embeddings, that's one approach. Not learnable cosinus embeddings. For the time position that we add with the arithmetic operation to the word embeddings. You could also do actually the concatenation operation. So if the model is like made correctly, there is not something that is disadvantageous, then in that case the adding should work the same way as the concatenation. But again, this is place for research, so not really sure. Like, I think from some papers they say that the adding is a little bit better. Like, I mean, a little bit resource less intensive, but at the same time, I would say that you can just split the embedding size on 2, like hidden size divided by 2, and then that will be the same. So either add or concat. So that's something that you can also research. So this is method one. There is also method 2 that we will not do today, but maybe I can give that as a homework. That is even simpler method. The simpler method is just to use the same embedding table as the word embeddings. So learnable embedding table, same as word embeddings, where every index means the time step. So for our embeddings for the words, we have every index means different word, but we could do the same for the every time step basically. And Yeah, so that's about it for the positional embeddings, I think. Let's look at the last slide regarding what you can do with this. So there is a very famous paper that made a lot of headlines, like produced I think like a year ago or something. The language models are few-shot learners, GPT-3. So again, I emphasize that GPT-1 is not that different from GPT-3. I think they just changed a little bit of order of the layers, and of course the dataset is much bigger. So they have really powerful models that can simulate like almost any kind of natural language tasks, even some arithmetical tasks, mathematical tasks, and things that you would not think are related to the language. So I think just this part is good to show that the transformers do not have memory. So that means that the way how you define your inputs kind of makes the model like conditioned in different ways. So they say zero-shot learning means that if you enter your model, the first sentence, translate English to French, that is already the input for your model, basically. And then you give the cheese with this arrow, and you will get the answer in the different language, because the model have seen something like that in the dataset. And then the one shot is where you give the same task as an input plus one example, and then you give the example of that you want to have the answer, and it will predict the next word, or maybe multiple words, and then it will predict the and symbol as we do in our models. And then the few shot, it will give even more things. And the more things you give, the better the model works. And the way also is that you can imagine that if you have entered these things here, you can enter also here the beginning of some kind of book maybe, and you will get the ending of the book. You know, there are some books very famous that are not finished. The model can try to finish it. There's also, you can have dialogues, and then you can simulate personality of some person and something like that. And all of this is just the same model that we're going to build today. The only difference why it's not exactly the same model as our model is, first of all, they use the common crawl dataset. So we are using the very dumb, very simple Kaggle, or that's not Kaggle, but the recipe dataset with a few tens of thousands of sentences. The common crawl is just text, so plain text dataset of the size of 250 terabytes. So you can think that like I don't have any any hard drive that can hold that kind of dataset. So that's one thing different from our model. Another thing is that to train that model on GPU, it costs $4.6 million. So I mean, so they have a lot of GPUs on the OpenAI. So, and if you do that, then you get this model that they are trying to sell right now. But the architecture and the mathematics is basically the same as this one on the first slide. So, and we will try to build it. And it can be used also not only for language modeling tasks, but all sorts of other things. And yeah, so I'm just thinking that I didn't, so I didn't copy the latest results from my model, but I will add it later, but it kind of converges nicely as well. So if you have the template ready, let's start coding. So I will share the screen. It was a lot of intro because kind of if you don't understand the basics, it would be really hard then to code it. So here, hopefully it works. Let me check. I will try to do experiment. Oh no, there is a bug here. There is already a bug. So this should be dataset full here like that. I will just test that this works, and then I will drop it in the Mega and also for the classroom, because I had already pre-processed the dataset. So if you see, I already deleted all of the processing for the dataset. I made a little bit better processing, You can make your own processing even better than that, probably. So if I try to run it, let's see. Hopefully the download works now. And okay, there's something. Okay, so but it fails at a different part. So that's great. So you can fix that yourself probably, because there was just one line wrong. So I will update quickly the Mega and also the Google Classroom, because that, unfortunately, that small file was not correct one. But you can fix it yourself as well. Definitely, I believe that you at this point can do this yourself. So let's see. So the template file here, there should be this one. Okay. So I'm dropping into the Mega, it is copied. Now I'm dropping in here. So this is not really the same dataset from the previous task. You can use the same dataset, but if you remember last time, we discovered that our dataset was bad. There is a lot of, like, when we did the histograms, we see that there is a lot of undesirable things, like, I don't know, like half, like half of the numbers or something that is not desirable. And also, if I remember, there was something that was a lot of, so there was a lot of words that were repeated just once or something like that. So definitely should not train on the sentences where in the training set word is repeated only once in the whole data set. So that's why better to use the updated version. Yeah, so you should probably delete this file and update it. So now the template is fixed. So then the positional encoding already implemented for you. So that I already give you. So then the transformer layer itself. So that's something that we need to encode. So the transformer layer is on the first slide of the Jamboard. So the transformer layer consists of the those three parts. So the first of all, key query value, right? Query key and value. So there will be the, let's see how we could call them. Okay, let's call them just feed forward, or just like project key, torch, and linear. By the way, some models do this by one-dimensional convolutions. Some models do this by multi-layer of something. Some models can also do the keys with some kind of specific table that is predefined. So by some similarity metric, so that's also possible. But in this case, we will do this as simple as possible. So the simple way would be like that. Transform a layer. Okay, that will be fine. So there will be 3 times this one. So key query value. We cannot use the same for three times. Yeah, so the error that you get is correct arguments. So that because you have not implemented the model, that's why there is an error. So that is okay. So this will be. Then if you look at the equations in the first slide, you will see that there is the feed forward model. So self feed forward model, and that will be the torch and sequential. That feed forward pointwise green box can consist of, again, something that you want yourself, but in this case, let's add it like this. In features will be hidden size, here we have an actually option to reduce the hidden size or make it bigger. Again, research topic. So I mean, like, maybe not a big research topic, but still, I don't know like how much they actually researched this stuff. Probably they tried a lot of combinations, but maybe you can find something better. So this is just one nonlinear kind of model with the one. So there is a one hidden state basically. So this will be here, and then we need two linear normalizations. So by the way, if you cannot download the dataset, please take the latest template, because I think I just I had a mistake here. If I go back here, see the dataset full, there is models, so there should be a small update. Anyway, so let's keep here going on. So the one is then the self norm. So there is two norms, if you see, after the skip connections. So norm 1, torch and n, layer norm, and the normalized shaped, in this case, if we normalize it across every time step, would be hidden size. Again, maybe there is a better way to normalize these things. So there is two norms here, so that's great. I think that's it from the learnable parameters. While you catch up, maybe I will look at the, I remember that GPT-3 had a little bit of reordering of things, or GPT-2. So we can look at that model, if I will find it. At least the images that I find look the same way. The only thing is that the layer norm is in the front there. Okay, so maybe I will drop the also in the Jamboard a little bit updated version that we can follow on the slide number 6. It's like basically very similar version than on the slide 1, a little bit, just few changes, because they kind of found out that that is a little bit better, I guess. One of the changes is that they use YellowRobot here. So the YellowRobot is like kind of ReLU got from I think from Gaussian function, like the normal distribution function or something. Maybe I'm mistaken, but I think it was something like that. So that's Gaussian, yeah. So that's really that's not too different from leaky ReLU at all. So but just because in that image we have that one. Okay, so that's great. So that part is okay. Let's try to first do the not multi-head, but just the simple attention model. So here, to get the simple attention model, we need to do following. So one is, I guess, it would be nice to define here batch size. So remember, the batch size cannot be taken from the hyperparameter, because we can work with different batch sizes. Maybe the last batch size will not be the hyperparameter batch size. If you want to run it on the production with a single sentence, again, there will not be the batch size. So here will be the sequence size. The sequence size is x size 1, and so just to define it, so the x shape is the batch comma sequence comma hidden size in this case. Yes, so that will be the shape here. And I'm just defining these parameters to help out a little bit later. So first of all, so the key value, self project key value forward. So we'll start by calculating the attention equation and then do the other parts. So here the x comes in. Yep, so the x comes in, that's it. So then 3 times q, qv, qv. And I guess I need also already to post to the Jamboard the first part. Because I will need to scroll a little bit. So this is GPT-2, I think, GPT-2. Okay, so I posted that to the Jamboard slide number 6. Okay, so that's fine. So we have those 3 values. Then we can do the equation. So attention. So we'll call this attention row because this will be before the softmax, because we want also to mask, to not allow to look in the backwards direction, and to mask, I will show you just in a second how to do that, but here we'll do the equation. So the equation is the q dot product with the k, and for the k we will transpose the last two dimensions, -2, -1, or another way. So with sequence and hidden size, we are transposing those last 2 dimensions, and then we divide it by the torch sqrt of the x size. By the way, you can just put a hidden size like that. Yep, I think it should be fine, except this is not a tensor, so maybe better to get it from x size -1, or let's say, yeah, -1, like that. So we have the equation implemented partially here. So the full equation then is with the attention of the torch softmax attention row dimension -1 over last dimension. So that would be the full equation. But we are missing something, because if we leave it like that, okay, we're actually missing also value here. So let's say there will be the out. So the full equation would be actually to have this one also dot product with the value. But if we do this, then the model will immediately learn to just copy the future, because we are trying to predict the future and we already see the future. So to avoid seeing future, we need to have a mask here. So to mask the attention, I propose to do following. So let's see. The best way to do this would be mask torch triangle. So there are upper and lower triangle. So I want to look at the lower triangle, and it will make the it will make, I think, the upper triangle as zeros, and leave the lower triangle as the values as they are already. So I will also debug it just in a second, so you will see how it actually looks like. So this is 1. Then there will be torch 1s. So we will construct the matrix here. The matrix will be sequence size, and we need to move it to device like that. So that's one part. Then also we have different length sentences. So it doesn't make sense looking in the future for the sentence where there is no future at all. So for IDX in, let's see, length in enumerate lengths. So we go sentence by sentence. Sentence by sentence. And then we will mask. So for each of the, so then for each of the samples, mask IDX, that is the batch size. So then in one direction, we'll make everything that is over the length here as zeros. And also to the other direction. So we don't want to have option to look in the future. And also we don't want to predict anything in that region. So that's why we do these things. And then the last thing is we need to somehow modify attention row. So let's call it attention mask, where we'll have the attention. So let's see. We could do this in different ways. Okay, one way would be to use attention row and use the masked fill. Masked fill means that those indexes that will match these indexes of mask where they are zeros, we will enter different value there. So the value should be in those places minus E8, for example, E9. So that means that the softmax with this negative value, like most likely will be 0. Hopefully it is possible also to write this kind of equation in a different way to ensure that 100% it's 0. But in this case it will be enough this way. So then the attention mask goes to the softmax like that. And in just in a moment I will try to also look if the visually if this is what we want here. So that's good. Okay, so while I will be a little bit scrolling, I will drop this into Jamboard as well. So I dropped that into Jamboard because I want to make my code in the way that I can test it at least a little bit. So to test it a little bit, I would like to also create the embeddings. So self, so there will be the pos embedding. Maybe I should write it project pos embedding torch torch and n. Yeah, so line 139 is like you write in the chat, because that, if you remember, so the same thing that we've written here can be also written with this kind of Python syntax. If you remember that, we can have something like that. So that is just a kind of lambda expression of trying to select all of the indexes that match that value from the array. So that is correct. So torch embedding here, the num embeddings should be the data set full max. Okay, I don't have autocomplete, unfortunately. Max classes tokens. So that is something that we calculated last time as well. And embedding dimension should be hidden size, of course. And the same for the so that, oh sorry, the first one is not positional embedding, that is word embedding. Word embedding, and the second is position embedding. And maybe you just added W and E like that. And for the next one, we have the max length. Hopefully that will work. So we have those two embeddings, and then we will construct the transformer. In this case, we will just make it with one layer, but in a second, so maybe we should start just writing as a proper transformer. Okay, so let's write it as proper transformer. Just a second. I want to check it a little bit. Okay, yeah, so transformer. So it's not finished, by the way, the transformer. I'm just trying to write a little bit of code so I can test it. So torch and n module list. And here we could, let's see, so there should be iteratable list. So we could make it as transformer layer for in range of the transformer layers, like that. Hopefully that is correct. And the last thing, I think we could add like final fully connected layer. That's just a like safety measure to improve the logits. So we could have, let's say, a fully connected one that will be torch and linear. By the way, I think in the implementation that in that paper they don't have it at the end, but I do not like having the layer norm dot producted with the transposed embedding matrix, so I'd better do this. So in features, hidden size, out features hidden size. Okay, so this part should be also okay, hopefully, for the model. And then we'll try to finish a little bit of the model so we can test the transformer. So here again, there will be important equations coming up. So the important equations that are coming up are the following. So one is that we need to have the position indexes, like, so we want the indexes for all of the sequences 0, 1, 2, 3, 4, and so on. So to get those in the shape, so we want actually this to be in the shape of, so we want this to be in the shape of the batch, comma, sequence. And then when we pass it to the project positional embeddings, we want to get the shape of batch sequence hidden size, and the embeddings, I mean the positions 0 to n are the same for every batch sample, also for those that do not go that far. So for example, if you have some samples only with 4 words, we will still add all of the extra words, but we will mask them later. So again, could be improved maybe, but in this way just parallelizable. So pos id xs, so these will be the position indexes, torch a range of 0 till the maximum length. So the maximum length may be the easiest, so the okay, I will just write it in this way to ensure that you understand better what I mean here. But in general, the maximum length can also be extracted from the index 0 because the packed sequence must be sorted by maximum length. So torch max, hopefully this will work. So to device. Then we have these guys already. So if all the embeddings are the same size, we could pass them first through the, so we could pass first them through the embeddings, or we could do the other way around. So let me think. So we have sequences, we have the index. Okay, let's do it this way. So there will be the embedding or P embedding, positional embedding of self project P embeddings forward of the position indexes. That's first thing. So then I also would like to unsqueeze it. P unsqueeze by dimension of this thing. So now I have the positional embeddings as those hidden sizes. That's fine. I'm just thinking, should I need it actually? Okay, I don't know. Maybe I need unsqueeze. Maybe I don't actually. So unsqueeze once, unsqueeze twice. So what we have here is right now the sequence size. Then we will have the 1 by 1 sequence, and actually not like that, but we will have the 1 sequence hidden. And that's why I don't need to do this twice, like that. And the next line, we should repeat this many times so that we have the same thing for the whole batch size. So there will be the position embeddings of expand, or we can use also a repeat probably. So the length, so this will be the size. Do we have, so, oh, I already didn't see that I have problem here. So there is embeddings written, but this should be project W. That is one mistake here, a little mistake here. And the other thing is we can expand it to the same size as this unpacked one. So I will update that in the Jamboard. So this line also was mistaken. Okay, and now the final z vector that is coming in the transformer is the it is the x unpacked plus position embeddings, like that. Hopefully it will work. And now we need to go through the transformer. So for layer in self transformer, and here there is a little bit tricky things because transformer gets 3 parameters, at least in this case, the x, length, and attention, like that. And the attention in the very beginning will be none. Layer forward, and here the z, actually this will be z, length and attention, like that. And if there will not be bugs so far, then I will drop it in the Jamboard. I will add here some breakpoints just to show you the masks as well in a second. So if I debug it, okay, I got some error here. Let's see, what is the error? SQRT is not a tensor. I don't like it. So okay, let's use not torch but numpy SQRT. So because I don't want to convert that to tensor every time, because you can actually pre-compute it probably. So anyways, so that small part was changed. I will also double check if everything else works, and then I will add this to the Jamboard. Okay, the masks did not work. That is not cool. Yeah, the mask did not work because, of course, here we have just the template of the mask for everything, but we need to select the lengths for very specific masks. So here, for every batch sample, here we don't have the batch sample. Here we have just the sequence, comma, sequence, right? But after this operation, where we apply the same mask for every batch sample, we have batch, comma, sequence, sequence. And here we are interested especially for the batch because every batch sample have different length. That's why we need to add this on this part. And also here we can have E minus 9 for these guys. So there is another small bug here. I will also mark those parts in with the red that I changed. So there's not a lot of parts, just very few. So okay, it worked so far, good. I just want to show you how the attention mask looks like. So if I select data, numpy here in the debugger, and just take the first sample, then I get 18 by 18 matrix that looks something like this, where you see that it pays attention to different parts of the sequence. So for the first time step, it has only the first input. Then for the second, there are 2 inputs. Then for the third, there are 3 inputs, 4 inputs, and we go on forward till the end of the sentence. So that is our attention matrix here. But also, if we look at the example of the last sample here, edit -1, it should be smaller. So let's see, the last sample is just 2 words long. And the two words long sample means that here we cannot look anything in the future here on this part. Also, I want to double check something else here. Okay, there is definitely a bug. It should not nullify 0, so here should be the whole set, not the 0. Whole set of the like whole row, it is the whole column. So let us check again. There was another small bug here with a 0 that is not needed there. And again, if in your case, when you are debugging this, it should be done in this way, that you look at the matrices and analyze them. So let's see what is now. So this is the, so this is interesting. This is very interesting. Okay, so for the first 2, this is great. For the next ones, this is not great. This is funny. of course, because in those parts it is the same as it is. Okay, let us think. Maybe we can improve the situation. Yeah, I did not notice that after the softmax operation, of course, if all of them are just e minus 9s, they will be equally distributed. But that is not what I want. But no problem, I will just quickly fix it. So for the first two, it was great. For the next ones, it is not great at all. So the better way how to do this maybe would be okay, let's change it a little bit. Okay, let's change it in this way. So first we can use here float minus infinity. At least in some PyTorch versions before, it worked really nicely by nullifying the softmax, but at least in my version it doesn't work nicely. It just produces NaN that is not good. So, and then to remove the NaN, we can do after the attention here, again the masked fill, where we can check that, or we can actually do this in a different way. We can just, there's not necessary masked fill, we can use attention, where the attention is bigger than 0. That is all good parts, but we want to look at all bad parts. By the way, if I would do in this way, it would not catch the NIN, unfortunately, like that. And then we can actually set all of those values as zeros. So we nullify them. Hopefully it would work. So let me check. That large negative value also can work. It's just that I really don't like that it kind of like continues living after it should be already finished. So here, this would be a better example. Yeah, so this probably means that we have length of 3. So you can see that we have length of 3. So we have a sentence with 3 words. For the first word, we see only that one. For the second, this one. And for the third, this one. Actually, this is a sentence of 4 words because it's predicting the fourth word in the third position. And everything else is zeros that we want. So that's great. Yeah, so I will update this in the Jamboard just in a second, and I will mark those few parts that I changed. So I changed the NP SQRT. So that's one thing I changed. Then I also changed the infinities. And I added the attention at the end. So that's great. So I'm adding that one actually in the slide number 6 with a little bit of updates here. And for the slide number 7, I will also add the forward pass to the place where we got it so far. And just in a second, we will finish the whole forward pass. So that's great. Okay, so we have the attention calculated. That is good. Then I think only the easy parts are left to do. So first, let's see what was in the model that they presented to give us. So first is that they want to do okay, I don't want to like so the order of the layer norms, you can do it as you want, but like I will just keep it with the original, I think, from the first slide, but you can change the order. It's just because I don't want to introduce another layer norm in the model. It will just confuse you. So, okay, we'll do that in a different way. So there will be x1 here, or let's say out1, and this will be x plus the torch dropout of the attention, or basically the out that we already have here, and the p probability of dropout is this one, and the train is self-training. So remember that normally dropout is turned off for most of the models, but for the natural language models, maybe it's good to leave it on, so it gives you more natural outputs. Like every time when you interact with the agent, it will give you different kind of natural language sentences. So that's one. And then let's see, so there will be out1 norm. This will be then torch norm. What is the name? Norm1, right? Oh, sorry, self norm1 forward out1. So that's first part. Then the feed forward network. Out2 is self feed forward out1 norm. Then again, here we have the skip connection. Out3 will be the so we are skipping from out1 norm up till out2, and then the last thing is again the norm. So actually that could be then y prim out self norm 2 forward out3. So that's the equation from the first slide. If we want to change it to the sixth slide equation, it's not too difficult to change it. It's just need to reorder a little bit and add additional layer norm to the model. But I don't want to do this now, so we don't need to return to something that we already did. Okay, so again, I will mark some of the things here. By the way, I should test it. I need to test it if it works, if there is no bugs. If there is some bug, then I should fix it now, otherwise I will have to update Jamboard again. Okay, it works, so that's great. So that part works. So I will update the Jamboard. So the transformer block is kind of ready. So that is the very basic transformer block. There are more advanced as well. So then the model itself have multiple transformer blocks chained together. So that is also working already. And the last thing is then to pass it through the last fully connected layer, I guess. Yeah, so let's do that. So there will be the so we should somehow pack the Z. So Z packed, padded sequence of Z lengths. Again, I do this because every sample in the batch is different length, and if I don't do this, then we need some other way to concatenate all of them together, and like this is one of the easiest ways to do this. So then the y prim logit will be the self fc forward of the z packed data. Yeah, so that will be fine, and then we will need to have that one dot product with the self embeddings, not embeddings but word embeddings, project v weight transposed. So that's the same as we did before with the models. So it goes through the same word embedding twice, in a forward direction and then also in the end of the forward direction. So in the very beginning of the model and the end. So that's good. And then the last thing missing here is the softmax for the prediction of the word. By the way, you can do this also for the character level, you know, like predict a next character, not only the word, or maybe parts of the words. So the tokens of the parts of the words is much better than the full words, because some parts of the words repeat more than others. So back padded. Hopefully this part is also okay. I will double check it. If it works, then I will drop it in the Jamboard. And I also return here the attention matrix, by the way. So the attention matrix is something that is really interesting that you can look later when it's like trained, fully trained, or during the training. You can like summarize over different layers what they are paying attention to. So this seems to be working. I will drop this also to the Jamboard, and then, or maybe at first I should try to run it fully, see if it gets through one epoch already. So this should be theoretically faster than LSTM as well. Oh no, this is one of the not coolest errors. So this means that there is, oh no, this is not the worst. I was thinking there is interruption in the gradient, but I can fix it. So in line 145. So I will check this as well, fix that one as well. But we are quite close of finishing it. So line 145. Train param. So there is a self-training param. So that is living inside the torch NN module. So inside the torch NN module, we have the self-training, and we are inheriting that from that. And you can enable this by using the model eval. Remember, that is when the training is off, or model train when the training is on. So that's why this flag is going from there. But there is another problem for me. I will quickly find. So there is a problem of the in-place operation of the softmax. They say that I should enable anomaly detection. Well, we could try to enable, or if I know that softmax is only used at that place. So I used it actually twice, so I will try first disable softmax here and see what happens if they have the same error. If I don't have the same error, then I know that that is an attention problem. So that is attention problem. So let's go to the attention model. So it don't like some kind of in-place operation. What is here the in-place operation? So I probably this one, I think. Let's see. So if I comment this one, let's see if I run it again. attention mask, right. Okay, it works, well, except there is an N because I did not delete it, but it works at least. So I need to change this line a little bit. I was thinking that it would work with this one, but it doesn't. So masked fill, and here we'll use the same thing as above. Value is 0, and hopefully now it is not in place operation anymore. Okay, except what is this? So okay, like that. Okay, hopefully now it is correct. I will try to run it. And if I get like positive loss value, then it's working, and then I can update the Jamboard. And I get negative loss value or NIN, which is not good, which is strange actually. So I need to fix it. Just a second. Try to look how to fix it. But we can find it definitely. It's not the end of the world. So so far the gradient goes through everything that we need, but there is some kind of bug of that we're getting the loss values as NIN, probably because we are playing with infinities there, but we'll see. So I updated the Jamboard as well for this small change of the masked fill. I know the problem. The masked fill did not return something, so I need to do this like this way. Okay, this was the problem, and now it will work. So I will update again the Jamboard, this poor slide 6 that we update so many times already. Okay, let's see if I run it again. By the way, if you have any questions at any part of the code, I really like that some of you are asking the questions and I can help you understand. It's better to ask a question about some part of the code than don't ask the question and then don't understand anything. So basically, the loss is working and the accuracy is improving. So that's what we want to see. And I added the code to the Jamboard already. So if you run this properly, like with the GPU, for longer time period, basically one thing that I could advise you is not to run everything at once on GPU with maximum length, but try first, let's say, with 10,000 sentences or something like that, or let's say with 1,000 sentences. So what I mean by that is you should change the hyperparameter of the with a CUDA with 1,000 sentences. So it is like this. So if you run it with this kind of hyperparameter, firstly, if you run it with the full dataset, it also will work. But with this kind of hyperparameter, you should get quite soon something like this. This was run like only so not for a very long time period, but you can see very nicely that the losses decreases and then the accuracy starts to increasing, and the outputs of that thing. I also kind of copied some of the outputs. That was not fully trained model yet, but if you see that they make at least some sense. So like the predictions of the recipes, you know. So the outputs should at the accuracy of 1,000 word, 1,000 sentence dataset, the accuracy of 56% of the 1,000 epochs. By the way, the 1,000 epochs works really fast because this model is much faster than RNNs. You can see that here, for example, is the turn fish onto work surface lightly, dust, molds of floor, crust. So basically there is some kind of a little bit of sense there. So sugar, bourbon, flour, egg mix at medium speed until skinny, smooth, something 5 minutes. So smooth gets blend through vegetables very light. So anyways, this is not perfect definitely, but at least it learns something. So it is a 56%. What I will do, I will train model with the whole data set for a few days probably, and then they'll add homework where you can try rollouts probably, and or you can train your own model. So that's one thing. So but we're missing the last part of the equation that we have not yet looked at, but I will show you in a second, is the multi-head attention. So here we just did this part of attention, but we need to do this kind of attention. So to do this kind of attention, there is one easy hack how to do this. I will show you. So to change this to the multi-head attention, that's why I added the batch size here as well. Or maybe we even don't need the batch size, but that doesn't matter, so better to have it. So one would be to split the K, Q, and V in multiple parts. So to split it, so right now these are in the shape of, so if we add here, so the shape is like this, but we want to have the shape of the hidden size sequence, and here we want the shape of the transformer heads, so heads like that. But in order to reshape it in this way, we will also need to divide it hidden size by heads. And to do them, maybe we could do it like K view batch size, or it could be also -1 here, but sequence. Okay, so yeah, sequence, first sequence size, then we will split first the hidden size, and then we will change the order. So then the transformer heads, then integer divided by hidden size transformer heads, because otherwise that will be a floating point value and it will not work. So, and then we will do the transpose of the dimensions. So let's see, so 1 and 2. So the one dimension is the sequence. Basically, first we have actually first after the view we have this kind of situation where there is a sequence, heads, hidden size divided by heads. Then I shuffle those two elements in the middle, and I get it out like that. So, and then I repeat this 3 times. So for the query value query. And the nice thing, what happens here is that no matter how many dimensions we add in the front, we are only working with the last dimensions, and that's why it will still work. So let's see, so this all stuff should work the same way as before, hopefully. Except there will be, so we will need to somehow have the out vector in bottom part as in the same way as it was in the beginning. So let's see, so the out vector, first we will do the opposite what we did before. So out vector should be shuffled with those dimensions 1, 2, and then the next thing is we should reshape it as it was before. So out, the one thing we need to add here is continuous, because If you don't add it here, we already shuffled a lot of things and added a lot of dot products, and the memory is probably not in the same block. And if the memory is not in the same block, it is not possible to call view function. It will just not work. So then the batch size, because the view function is just working with the same memory block. So this one, then the sequence size, and the hidden size. I think that's about it for the multi-head attention. Let me run it and see if I don't have a bugs. Maybe I have, and then I will need to fix it. But in general, as you see, this is not difficult to implement. The only, like, if you would start implementing this way, that would be like real, like a kind of brain squeeze, you know, because like if you start thinking about 4 dimensions, then it's like even more harder to understand. So anyways, this works, except there is one problem. This works, but so first of all, I left in this code, I think, in the bottom part, image IO. So here, if these lines doesn't work for you, please install pip install image IO. And these are saving the first and the last attention map. I'm not sure if I added those, if maybe I did not add those for your template. But that is something that you could do to save the attention maps and then explore them as well. But in this case, we also need to fix the attention map. Just a second. Sorry for scrolling. I will quickly find the place where I was working. Okay, here. So the attention maps could be probably one way. What we could do is attention that I want to return. So first of all, I want to detach it, because that I want to use only for diagnostic purposes, not for the training. And the other one would be then, let's say we can have the mean, or let's say max even, oh no, not better mean of the dimension 1, which is the head dimension, because we have this shape here. So we will convert this one back to, so actually this is not like that, but sequence by sequence. We will convert it to just batch sequence by sequence. And then we can display it nicely visually, how the attention maps look like. Okay, so this is the last part regards to multi-head attention. So the multi-head is just these 2 small parts added. So I will drop those into slide number 9 probably. Again, you already saw in today so many things that you can explore and change and even research, like starting with the positional embeddings, the attention mechanism, the architecture, so a lot of things. Anyway, so this is working now. I'm going to train this properly for a couple of days, and then I will give you the homework. Tomorrow we will not have the session. Tomorrow I have a different plan, so that's why I cannot do a session tomorrow, but we will meet next week. So the next week we will have the last 2 sessions, and the homeworks I will wait till the end of the May. I agreed with the university that I can grade them till the end of the May, so the end of the May, the last deadline to pass this course. If you have so many questions, try to get me, but like I'm also quite busy, but I will help out, especially if you have plans of keep working with deep learning research. I'm open to discussion. So that's it for today. Hopefully that was fun and interesting, you know, like building the state-of-the-art models. Just need to add a little bit more memory, up to 250 terabytes, and a little bit money for GPU, and you're good to go. So that we'll meet next week, right?